So next we have Claudia here. She's going to, from GM, she's going to talk about the bridging communication gap between humans and robots. There you go.
Okay, right. Hi, everybody. Thank you for having me here. It's my first time. So I also will say a few words about myself. Let's see. Yeah. I have some academic background for some years. I got a PhD at the Hebrew University, and then I spent some research fellowship positions at Bar Ilan, University of Massachusetts, and University of Haifa. And then I switched to industry, first in Samsung, and for many years in General Motors. I'm part of the R&D organization. And what I would like to talk today with you is about what are these machines, these robots, about this big robot called autonomous vehicle. And what is this gap that I believe exists between what a user understands the robot is doing and what the robot itself is doing by itself. So let's start by this big picture. And if you want just to be a bit interactive, you can tell me what you see here beyond just a Cadillac dashboard. If you have any idea why I put this picture in here. Anyone wants to volunteer an answer? It is explanatory? Okay, so now we see that it depends on the user attitude, right? Okay, so my point here is that when you look here, you see a lot of different systems. So if we look at this as an engineer, you will see that we are very good at creating all kinds of systems, rich variety of options, functionalities. But if I'm looking at this from a user perspective, what I see is a bunch of separate systems that are telling me, if you have a problem, here we are. We have a lot of buttons you can use, but you will need to configure the right configuration for yourself, and you will find out what is the right solution for your problem. So if now we look at this as a big robot, I'm trying to see what the engineer is building for the user and how the user is going to use this robot. And when we look at this approach from an engineering side, what you saw in the previous picture and in general, you can understand that the ways the human-machine interactions are being conceived is that a user is operating a big system, right? And it's not more really a continuous process of time. It's really for very limited time periods. You're using your air conditioner for certain times while you're driving. You might have an app that contacts you maybe when you are not in the car. Also, all the inputs that you saw before are manually entered to the car. There is no proactive behavior from the car to the user, and all the systems have the same size and form. And now the question is, or I ask myself, why is it that way that we are building these big systems? And it took me some time, a lot of reading of other domains besides AI that have been my main area for many, many years, to really understand that when we started doing automation, we really wanted to replace physical tasks for very well-trained people, right? So we were talking about pilots, we were talking about plant operators, and they really had to operate a system. And also they only talk about physical spaces. But now if we look at the evolution of users, technologies, and so forth, robotics, obviously, now we are talking about users that can be anyone, right? It could be a child, it could be a very old person, it could be a child that is driven by an autonomous vehicle. It doesn't have to be a person that have a driving license. So now we are talking about anyone can be a user. We are talking about physical domains integrated with digital domains, and we don't have to really divide the task. It's not either the machine is doing something and the person is doing something else. We can talk about collaboration. So in some sense, we are moving from being operators of machines to really consumers in some sense of services. And then the question would be, how do us as users, as consumers, consider those machines? So I was thinking, we have this talk about Bosch, but you can think about any other appliance that you bought for your house, right? It's automated in some sense. So you buy a fridge and you expect that fridge to work as you expected, right? But when you buy or you use an autonomous vehicle, the situation is very different. And the reason is that that car is making decisions under uncertainty, right? So it's not that the car is going to perform exactly as an electrical kettle. Each time you put water and you click on the button, the kettle will boil the water. Now, if I am going to be inside an autonomous vehicle, the traffic might change. The vehicle is predicting what this traffic is going to do. Weather might change the visual of what the sensors are looking at. Sensors might fail sometimes or work at different confidence levels. And now the question is, when I as a user are driving that car, how I interact with that car. So from the mathematical point of view, obviously you all here know about reinforcement learning and optimization of utilities. But from the user perspective, it's not enough to tell you, be sure we are making the optimal action we can, right? Because that optimal action, it's not always deterministic most of the time, and it's therefore not clear. And that's the point I want to make here. So what we will do with all these systems, with those robots, for example, that I'm making decision under uncertain conditions, and now there is a user that wants to accept the robot, wants to trust the robot, wants to use it. So we are, as people that make those robots, we want the users to use those robots, right? And the question is how we can make that behavior explainable to a user. So we don't have much time here, but I'm going to give you some highlights from two main projects that I have been leading at GM. So the first one is a joint work with Michael Baltaxe that we published this paper, if you're interested in reading more details, in IEEE Intelligent Vehicle last year. And the idea here is that even before I come to planning, to decision making, we have perception, right? So assume that you have a convolutional neural network that we know that is a black box, and someone tells me that he already trained that network. And that neural network is classifying different situations. And he tells me that he trained that network with very high accuracy. Now the question is, do I get convinced that because you tell me that that network has high accuracy, I should do whatever it tells me to do? So you can think even not just a usual person on the street, but just let's say a plant operator in a manufacturing plant, okay? So now we want to tell that operator to do something with some element that he gets in the plant, and he needs to decide what to do. So far he was using his own mind and he was inspecting that product. And now we want to use some neural network to recommend that person to do something, either throw it away or use it. And now the person will come and say, but why should I do what the system is telling me to do, right? Why that person will collaborate with that robot. So let's see what we can do about it. So in this particular problem, what we said, you give me your best classifier, and I will adjust its architecture and retrain only these new connections so that I will transform that classifier into an explainable classifier. So if you can see the picture at the bottom, you see in the pink rectangle a classifier with all its layers. We are going to compute one specific layer that we will call the L star layer that will become the layer to which we will add a new node called the category branch. Sorry for the font changes, that's different computers, never mind. And then we will make that explanation into kind of a sentence that a person can understand. So basically, you give me your best classifier, I do some changes to it, and eventually what will come out from the explainable classifier will be the original prediction with some explanation for why it predicted the particular output. So here is the whole algorithm. We don't have time to go over all the details, but it's mainly about 5 steps. So first of all, we will need to define some language of explanations, right? For different domains, we might use different explanations. Once we have that, we will need to find out which one is that layer that I want to connect to. That will be my anchor layer. And we have some formulas to compute how well it correlates to the explanation, to the semantic labels we are adding to the system. So remember, the classifier is originally computed for predictions, not for explanations. So we need to find that layer. We will add the new nodes, then train only the new connections. And finally, we will get these explanations. So I'm going to show just two results from two different domains. So in one case, we had another project at GM working on adaptive driving, and also Ruben is here in the audience. He was part of it. And for this presentation, I'm only focusing on one particular classifier neural network that we have used for that project. In that classifier, what we had to do is to give any driving scenario that we have used for that project. We wanted to predict if the user is going to feel comfortable or not based on those driving conditions. But if we put all this aside for the moment and just focus on the classifier, we want to know now, why is the classifier predicting that comfort or discomfort of the user? So if I just got the original classifier, the only thing I will know is that the person is predicted to feel discomfort, but I never knew why. So in this case, we extend some language of explanations in the domain of traffic, pedestrians, open road, and so forth. We computed that best layer L star, so I'll make it faster. And as you see here at the bottom side, we have three cases. For these three cases, the classifier would give the same answer. The prediction is the user will feel discomfort. But because we have trained the new explainable classifier to explain why it was that prediction, we can distinguish between these three cases. They're not similar anymore. In one case, we have a problem of traffic. In another case, there was a jaywalker. And in the third case, there was an issue of a cutting-in vehicle. We also applied the same algorithm to another public available classifier that was able to predict in which lane each one of the vehicles in a certain boundary box are going to be in the next time step. So the original classifier was able to classify if a vehicle is going to make a left lane change, right lane change, or brake. But again, we didn't know why. For this case, we have a multi-label concept of explanations that allow us to explain with more than one concept the same event. And interestingly or nicely, what we have here is because we have such a vector to explain the predictions, we can also say that something happened because, for example, there was a cut in and there was not a left lane change. And it is known that for humans, usually when you require an explanation, you want to get contrastive explanations. So if I explain to you something, you would like me to say why something A happened, but also why B didn't happen. Here I have a few very short movies that don't move. No, it doesn't. The whole thing doesn't work. What you see here is the blue circle that shows our ego vehicle. All the red, thank you. All the red circles are the real traffic. So what you see moving is the actual data that came with the paper, the one that we didn't work on. What you see on top of the graphs are sentences that come from our explainable classifier. So for example, in this case, if we could see the movie playing, the blue circle is making a left lane change into where he's now, right? It came from the right lane change and it go to the other lane. And the explanation was that left lane is faster than ours. So that explains why the prediction was for the blue vehicle to move to the left. I want to show another thing. The next, yes, please. Just in the few minutes that we have. So now that could be also understood as part of perception, but now we get to the more difficult part of the equation, that is the decision-making, right? So now the vehicle is going to plan its driving maneuver, and now we are the people being passengers in that vehicle. And the question is how the vehicle can explain its driving maneuvers. So at the moment, what I will show you here is that we have two questions here. One is to understand how we compute the explanations on a planning system. And the other side would be to understand what humans require, what information might help them understand what the vehicle is doing. So I'm going to show some results from very large user studies we have been running last year. And what you see here is some movies we prepared with Cognata, that is an Israeli startup, for those that you don't know. I don't have the movie here, but you see a snapshot. For the first study, we recruited more than 1,000 people. And online, we distributed all these movies that we have a total of 10 movies. Each person watched 6 movies. And we have different types of driving. We have different age groups. And basically, what we wanted to do in the first study is just to understand under what general conditions a person might need more information that whatever he sees in the movie is not enough to understand why the vehicle is behaving in certain ways. And what we evaluated is the people comfort and understanding through some online questionnaires. Okay, so in the first study, we compared between general explanations and more specific explanations. And we found out that specific explanations can really help. So they help to increase comfort, although a bit slightly, a bit small increase. And they also help to reduce misunderstanding. We also saw that age and frequency of driver really have an effect of the explanation. So people of different age groups will react differently to different types of explanations. And finally, when we ask about the reasons for discomfort, we got these 3 main reasons. So one is that we didn't present any HMI display while they were watching the movie. But more interestingly, is that people were looking for what the vehicle was about to do and what was the risk of the situation. So we started to design a second study where we took 6 lane changes cases that were interesting, that might cause some concern on the side of the user. For example, overtaking that van when there is an oncoming vehicle coming from the opposite side. And for each one of the 6 cases, we also added the HMI dynamic display that you see at the bottom. And now, because of the reasons of discomfort, we have a set of 4 explanations. One would be just the HMI. And then we have an explanation of type risk and an explanation of type plan next. Those explanations were handcrafted. And currently, we are in the process of computing that information from a real planning system. Okay, so one of the results that we saw is that if we look, for example, in this particular driving case in an urban scenario, we look at the number of people answering any one of the possible answers to the question, for example, level of comfort. So we can look at the effect that has any one of the explanations relative to the HMI. So if you look just at the top part of this graph, you will see that we could find at least one explanation different from HMI that has an increase that is significant in terms of increasing extreme comfort. In the bottom part of the graph, what you see is that we also find at least one explanation from our set that decreased discomfort very much. The only case that you can see in the middle here is the late merge. We didn't find a good explanation for that case, and maybe surprising or not surprisingly, this is a case where the lane is about to end and you try to merge very, very far away, very late. So actually you are pushing yourself. And obviously in the States, this is not so much usual. So culturally, probably they didn't like, so no matter the explanation, it didn't help them. But it's interesting to see that we can find information different from HMI that actually help the people. So now that we have all these statistics, the question would be, okay, so now you are driving, which explanation should I choose to present to you that helps you best? So one way to do that is you tell me what driving scenario you are driving, or the robot will tell what is the driving scenario. I can add some features of myself, like my age, and the trust measure I want to maximize. For example, you want to maximize the full understanding of the driving maneuver. So I can go back to the data and choose the explanation that maximizes that trust measure. I think I will skip that. I didn't mention this is also work that we published this year in IEEE Intelligent Vehicle, and it's joint work with Ronit Bastin. So you can go there and see the paper by yourself. And the last piece of work here is that so far we were looking basically at the explanations that were singletons, besides the risk and plan next together. But what about if we have a larger list of, we have in the previous slide, 8 new explanations. So we cannot ask people to answer all the questions for any possible subset of 8 explanations. So what we did is we went back to the information theory and we tried to find or compute the mutual information between the answer or between the length of that subset that we are evaluating and the maximal answer for that particular questions we are interested in and the subset. And what you see here is a bit cut. Okay, so I'll tell you in words. We compute the mutual information for all possible subsets for that list of 8 singletons of explanations. And you see first, the first row is the winning subset of explanations. And what happens in the third row that is very similar to the first one without the contrastive explanation. So what this means is that the contrastive explanation is really essential to be there in the solution because it increases the mutual information. On the other hand, if we have redundant information on the second row, we have risk and risk plus plan next, is not necessary to have twice the explanation about the risk, and therefore it got less value. So just to conclude, I hope I convince you that when we work as engineers, we expect some level of trust from our users in our robots. But when we look at the robot from the user perspective, there is a level of trust that is going to be established by the user when it works with the robot. And these trust levels are not necessarily the same. So there is a gap, and we believe that information can mitigate that gap. I also present to you the methodology we use to collect data and analyze user needs for information, and also supporting others in the literature. We also found that there's no single explanation that can be best for all situations, all people, and all types of maneuvers. But we did find that there are some specific types of information like risk and planning next that are not the current elements that we see in HMI displays, and they do have some positive effect on user understanding and acceptability. Thank you.